little introduction, little catch up.
Okay, cool. Right. So what we thought we'd do is we do a reasonably quick one on phenolic. Paul, because my computer's going terribly, Paul has had a quick look through. We were going to use these as little prompts, like a closed little webinar, just to discuss phenolic. Hopefully it flows. I think the DN is, Dave, you're recording. Should we just wing this?
I'm recording. Paul's presenting.
Yeah. So Paul, what I'll do is okay. If I just go like that, you just go next slide. Yes. So just keep your eye on me and I'll go next slide. And Gordon, even though we rehearse and train and practice, we wing gracefully. Hello, everybody, and welcome back to the E5 podcast. I am your host, Paul Meenan, and I am joined by my E5 brothers and tag team partners. Please introduce yourself and get the order correctly, and then we'll introduce our guest.
Hello, I'm JW.
Hey, it's Dave Watts, Sparking Ninja.
And hey, I'm Paul Scum.
And we are delighted today to be joined by an industry peer and expert and respected colleague from the electrical industry. Sir, would you introduce yourself to the audience?
Yeah, my name's Gordon McKenzie, and I've worked in the networks industry since 1985 and recently retired in September of 2021.
So just to put that clearly, in 1985, I was in primary school. Drinking bottles of milk, having naps, and not knowing about the horrors of the electrical industry. No, I'm only joking.
Well, I'd actually started my apprenticeship in 1980, Paul, so that's...
I was three.
You're only 2 years ahead of me, Gordon.
I was three. Oh, God, yeah, I look older than all of you. Right, okay. Well, thank you very much for joining us, Gordon. So what we're going to do is we've managed to hijack Gordon for a couple of these podcasts because we want to talk and debate a couple of issues that are really important to us all, and also raise awareness for those who are listening. Now, more importantly, if you are listening to this, thank you very much for listening and all that. And we're sorry we've been away for a while, but we said we'd only talk when we've done the research and got something interesting to talk about and debate. And these are debates, these are opinion pieces. But what we've done for those who are watching in the wonderful world of YouTube, this is in the format of one of our webinars. We just don't have an audience today. So thank you for watching. And if you are listening and you want to see more of what we're talking about, please watch the YouTube version as well when it goes on the relevant channels. Right, should we get on to it? So we're here to talk about something that I think me and John talked about over a year ago called phenolic. I do love that word.
We teased it in the code breaking webinars that we did. We teased it for 5 minutes.
They seem like a long time ago.
It was a while ago.
They were long. We need to do new ones when Amendment 2 comes out.
Yeah.
So yeah, phenolic, more importantly, a term that I think we called phenolic degradation. So if we move along on the old slide deck for those watching on YouTube, phenolic is, as John Ward calls it, Bakelite, but it's defined in a standard that we found as thermosetting plastic made from a phenolic resin with wood flour filler. Now, phenolic, I think it's fair to say, John, and you could disagree or not, it's part of the plastics family. It's an old school recipe for making of plastic using heat and compression and resins and chemicals. And over the years, plastics technology has moved on. And phenolic materials used probably, well, for decades and decades. I don't think it's used much anymore, other than in Kingspan, weirdly enough. Kingspan, you know the boards we get, the pink boards? That's phenolic material in the fire-rated boards. I didn't know that, but I was researching.
They're still making that now?
Yeah.
Oh, wow, okay.
It's fire. It goes. So you know when you get the fire-rated boards, they are apparently phenolic material. According to Kingspan's website, I will indemnify myself. Mr. Skirm, go on. You're looking intrigued.
We can still get what's the board? I can't remember the name of it now. The brown stuff.
Paxilin.
Paxilin, yeah.
Yes.
That's a phenolic, laminated phenolic product as well, isn't it?
Yes.
I guess the difference is, though, we buy it today, and it's time that seems to be the thing that defeats this material.
Yeah, it's possibly the definition may have changed as well. Maybe wood flour filler. Maybe they use a different filler now, maybe a more inert one.
Yeah.
Wood flour. I'm going to jump ahead then. I'm not going to jump ahead. I'm going to stop.
Okay.
Yeah, no, good, because Paul has control of the IT, so please move on. John, I think this was our definition. Now, we call this cut out the John Ward, purely because John was the one who noticed it has a human-esque face, doesn't it, John?
Yeah, the nice 2 eyes on the nose and the yes.
But it's a bit of an example of one. And I think what we were talking about when we teased phenolic degradation is, I don't think anyone says that phenolic material isn't a brilliant material. because it's lasted for decades and it's advanced and advanced and advanced. But over time and pressure and use and maybe change of external influences in the environment, it potentially becomes a hazard.
I think fundamentally things do become life expired, especially if you change any of their initial criteria or their characteristics. It's just a question of, if people proactively maintain the life of these items by replacing them, or if we just allow them to get to that point.
And that's a great image there, because you can see temperature has affected that cutout, because
Indeed,
the fill has started to leak on that wonderfully compliant BS951 clamp. Nothing wrong with it in the old.
Compliant because it was okay to a standard of a few years ago, wasn't it?
Yes.
Yep.
Gordon, do you remember fitting the 951 clamps?
They're actually non-approved as far as the network that I worked on.
No, I know, but they used to be. They used to be
because of the compression of the pulp, the soft pulp, the compression it sort of thing. So it's always been a bit of a bugbear, and especially for the DNO staff, because it was never something we normally had in stores, but they always magically appeared on the pulp cables. So
it's interesting. So for those who are watching, please watch our previous webinars on DNO coding, because we go through the whole BS951 history, which did allow the use on cables, Gordon, up until I think it was the early 80s or maybe 90s, but it got removed anyway, which is why obviously you don't see them anymore, and they use the spring toggle ones and various other things. But yeah, move on, Paul.
Okay, so a bit of video now, which I will play.
Yeah. Now this is a really interesting video, because obviously it's just a standard Mega. And what you can see is they've put some bolts in, engineers experimenting. And you can see there looks like a scorching or arcing. And with the Mega, you can actually visually see a little bit of tracking. And that's the thing with phenolic material. It can break down to a point where foreign bodies and materials can effectively allow parts of it to the resin film to break down, carbonize, and you can get surface tracking.
That's the key point. It breaks down, it carbonizes, and then obviously the carbonized, you get some kind of level of conductivity, and then you'll get constant tracking, won't you, at that point?
Got wood flour filler in it, doesn't it? Well, coal.
Yeah.
That's what coal is,
I think just one of the points to make with that one, Paul, for anybody looking at it as well, is there is no fuse cartridge in that particular holder there. So it had been removed. Yeah. So there's nothing between the blades there. The electricity that's in the path you can see between the two fuse blades there is occurring without a fuse being present.
That's pretty special. I thought there might. I didn't know that. That's wow. Okay, that blows my mind even more. But then again, Dave, from an electrician perspective, if you're on site and on the tools, the use of a Mega now expands. You remember the webinar you did on the hidden tests?
Mm-hmm.
You can expand this quite a bit, because I've been doing some recent testing and putting IR tests across GRP ladders and getting low readings.
Well, remember, we do use insulation testing for many other test types, the special types of protective measures, insulation floors and walls and stuff. And we can use insulation tests as long as we use them safely for an awful lot more work than we actually use them for. Indeed. You can use them for a lot of stuff.
And just another point on that one, Paul, before we go off it as well, is that what you're seeing there is the location of the breakdown, where the tracking's occurring there. And if you can imagine that when it's in situ, the ability to find that very localized failure there is out with the guy actually operating the fuse at that point, or anybody approaching the front side there. So it's a very localized failure between the blades of the thing. So as I say, one of the issues was always about how would you identify a failing cutout, or one that was in the process that had got to the stage where this was occurring. And that is one of the difficulties facing the industry, as the voltage indicators, the contacts trying to find a very localized area of failure can prove to be a real challenge.
I'd love to put a fuse carrier that's got this on it under a good period of load, and then put some thermal imaging cameras on it to see if there is any pattern that is completely foreign to the normal fuse carrier pattern.
I'll tell you one thing that this raises is this kind of just shows you you can see why when you're trained to pull fuses, and training is very important. And I've always said that every electrician should be trained on to work on this equipment. If you had a fuse carrier like that and you were just going to pull it under full load, you can see how quickly a huge arc flash or bang, and this is why the guys are trained, you know, isolate that load straight away, pull it using the insulated gauntlets. But more importantly, this is a perfect video that proves the point of visually inspecting after you've withdrawn it to make sure there isn't this form of damage. Now, I used to work with guys in my area, the old UK Power Networks, where when they did pull it, they would inspect the fuses to see if there was anything wrong before they reinserted it.
And they should do, because who else would do that?
Exactly.
And just again, Paul, looking at that's a very visual, granted, a very visual representation, and you can see the tracking there and where that occurs. But you know, that tracking is the primary concern, is that can track from phase to phase.
Absolutely.
Phase to neutral, phase to earth in a very, very small and localized area.
Mr. Skirm's gone dark on me. Forward, if you don't mind.
Right, next one.
There we go. So just in case people are wondering why we've disappeared for so long, we have gone down Pandora's we've gone down the rabbit hole and opened Pandora's box and found another rabbit hole and gone off into a quantum realm, and it's just gone insane, the amount of research that we've been doing and documentation we've had to read and correlate, and the DNOs and the networks themselves are insane.
It was surprising how many different other industries have done studies on any kind of phenol material and the way it behaves over time, and not exact studies on fuse carriers and electrical switchgear or anything like that, but other uses that this material has been used for. And there's this kind of thing has been reoccurring, and we've seen stuff from the 70s and even you know, well, I mean, this is
1961,
60 or 61, where they start talking about this material, and there's tracking here on a bushing.
Mm-hmm.
You know,
they identify things like copper trees where they look microscopically at it, and there's been a lot of work. Now, this is the earliest paper that I think we've ever seen. Ironically, and I apologize, and we'll probably do another one of these in a year's time once we've done more research. The trouble is having every single IEE journal takes weeks to read. But there are, we know on some of our other webinars we will go into on another day, that this stuff can go back into the 1800s. So the original discoverers and researchers of materials and insulators and all the rest of it. So we just wanted to show for the visual aid really of those watching on YouTube. There are papers first presented July 1961 at an international conference of materials where people identified and spoke, because years ago, good engineers would write a white paper, which is their theory and assumptions and their research, and then present it to their peers. It doesn't really happen that much unless you're doing masters and doctorates and stuff, but that's how it used to be done, and it's really, really good. And we found this old paper that looked at electrical breakdown by tracking. Mr. Skirm. Right, so what we got is just some images. We're gonna go through these pretty quick, just to show you some of the events that can happen from a breakdown of phenolic material, whereas if it's not dealt with or identified, then it can lead to our latter part of this podcast. Mr. Skirm, you can see obviously where people have been taking insulation resistance or continuity tests to try and identify these breakdowns. That's really important when you're investigating. Next slide, Paul. You see the damage as well, the ferocity of some of these intakes that have melted and the damage they've done. Now, I've actually attended them. What worries me the most is that three-phase one there. And that looks relatively healthy, but that's still obviously had a phenolic issue. And I wasn't aware, but some of the early GRP or grey plastic ones actually were phenolic as well. But let's next slide it.
Okay. Ooh.
Yeah, well, that one I think, that one had it existed. I think it's fair to say.
You say some of the earlier grey ones were phenolic.
Yeah.
So when did it transition to GRP? Because we've got the paperwork that basically we've got the evidence that says GRP is much more robust.
Yeah, I've written and I've asked, and I'm trying to pin down dates at the moment.
Okay.
The early GRP stuff was good.
Yeah, from our experience, we stopped purchasing around about the mid 1980s. I think we stopped purchasing the phenolic for GRP, but we continued to use up stock.
So maybe 90s.
Early 90s, I think.
Early 90s.
Still using up stock. Yeah.
Yeah, I think it's the point here we haven't really made particularly well yet is that if you get this tracking within that phenolic material, it doesn't end there, because the actual act of it doing that creates a conductive path. So then you get more current going through it, which of course then degrades it further. And then you get more current and so on until you get this sort of cascading failure. And that's why, and we've got these pictures here, it gets into such a terrible state, because once it's going, it's pretty much inevitable that it will carry on and basically destroy itself. So
well, it feeds itself at that point, doesn't it?
Yeah, that's right. So every time that current goes through, it's carbonizing that particular pathway even more, making it more and more conductive. So
that kind of leads on to this little beauty that we found, and this is all publicly available. So there is a High Court of Justice for Queen's Bench Division Technology and Construction Court at the Royal Courts of Justice in Strand, and there was a case which is again publicly available, and it was presented before Mr. Justice Ackenhead, and it was between 5 parties, and effectively there was a court case against parties and Southeastern Power Networks, London Power Networks, Southeastern Power Networks, and Eastern and Southeastern Power Networks. So basically the southern area of England, and it was all about the maintenance of the intakes, the cutouts, because of fires. Now on the screen you can see the kind of the introduction to this. So I'm just going to read it out for everybody, and it says, these 5 claims are for damages for negligence said to relate to fires in 5 sets of premises. So it was a group case, all of which started as a result of resistive heating emanating in what are called cutout assemblies. And I do like legal because they simplify it. Where mains power is brought into by cable into premises, it first goes into a cutout assembly, which is in effect a junction box with 1 or more fuses in it. From that cutout assembly, cables are then run to the electricity meter, where the amount of electricity consumed is measured, and from where the electricity passes into the premises. Since the privatization of the electrical industry, responsibility is now divided between distributors responsible for the bringing of power into premises for the cutout assemblies, and the suppliers who charge the customers for the electricity supply and who are responsible for the meters. The 5 claims are in nature of test cases, albeit they do not amount to group litigation. The overriding general issue relates to the scope and extent in practice of the tortious responsibility of the defendant distributors. They were trying to set some precedences here. That's I think what drove this case. Whilst there are also major issues on causation in the 5 cases, the duty of care owed by the distributors is properly admitted. That's a really interesting sentence. The scope of the dispute involves a determination of what, if anything, the defendant should have done by way of inspection, maintenance, replacement, or monitoring of the cutout assemblies. The generic liabilities have acquired the acronym RIMISI, which is replacement, inspection, maintenance, and some other. Oh, there you go. Repair, installation, maintenance, inspection of supply side equipment. So that's what this court case was about. When did it? And we mentioned this over a year ago in our last Diverted Neutral Current webinar, where we said, when do they ever knock on your door and come in and say, here, I'm here to inspect your cutout? The only people who really do are the meter exchangers or the electrician. So next slide, Paul.
Or when they had meter readers come in, the meter reader, which was working for the network operator at that time, would have had a look, wouldn't they?
Exactly.
But as I said in the webinar last, our provider, my wife gives readings over an app on her phone. So they've not been in the property for 8 years.
And it's a really interesting report, and I highly recommend. The reason we put it on the slide so that people can see it and they can look at it and go away and read it themselves. But it says on section 19, cutout assemblies come in different shapes and sizes, depending largely on the age and rating of the service and whether the consumer is provided with a single phase or 3-phase supply. The more modern ones are usually encased within glass-filled polyester, although historically other plastics such as phenolic were used. The oldest service heads have cast iron casings. These assemblies may have pitch or heat shrink plastic shrouding or neither within them, depending on the type of service cable to which they are being used to terminate. The very large bulk of cutout assemblies over the last 50-60 years have been manufactured by 2 companies, Lucy and W.T. Henley, although BICC and Pirelli had not insignificant share at least one stage. Interesting, I even mentioned phenolic in this. So they do talk about it. It is a brilliant CPD read. It's a heavy report, but we've all read it, and I think it's an absolute. Have you read this, Gordon? Have you?
Yeah, 90-page report, and the word phenolic appeared once in that. Numerous attempts to try and get some sort of visual, pictures or images of the cutouts that featured in the case without success.
Next. There we go. So this is a phenolic fire, very close to home, because this was the first week of my job. We had a DNO supply that had been melting for 4 days. The staff had been smelling fish for 4 days, and that's the result of it.
I think these are really important images, these, Paul, in understanding the tracking. So the failure mechanism there's probably something to do with the connection or the overheating of the blade, or some, you know, any one of the component parts within that cutout. The risk with phenolic and why it's so different for GRP is that it doesn't stay localized to that. So that overheating terminal then impacts towards the other two phases, L1, L2, L3, or towards the neutral. So the one of the first things, the steps that we took, was that you really couldn't do a partial repair on these. So it wasn't enough to want to take L1 out and replace it, because you've already probably got damage on L2 or L3 or towards the neutral without necessarily being conscious of that as well. But to see it as localized in that image there, you can see the heat source, you can see it very clear. You've not lost the building as a result of fire there. So it's a really good image of that one.
I'm amazed that the meter boards, which are supposed to be fire resistant, had burnt out to that degree. I mean, that's a significant heat.
It's a lot of heat.
Yeah, that is. So yeah, got very lucky there.
Well, I think that one of the things we looked at, Paul, as well, was I think when you see some of the failures, I don't know if some of the images will show that, but the tracking causes a melting, like an arcing melting of the brass components or the components of the cutout, and that's 1,000 degrees or thereabouts that happens. So it's generating a significant heat source.
I will say, when the DNO came out to this, it was about 9:30. They actually removed the old cutout, and it was still red hot to touch. It was very, very hot. Unfortunately, all they did was replace it with a GRP one. That's all they did. It was just like, oh, there you go. And I was like, can I have that, please? And they were like, yeah, I suppose. It's just phenolic. They burn out all the time. And I was like, yeah, that'd be really nice to have that. But yeah, that's the forward-facing image for those who are watching on YouTube. Quite a distraught first week of the job, really, that was. But yeah, that was kind of what opened my eyes to it. So
did the electricity network provider provide you with any guidance on how to monitor, identify, or limit this thing from happening? If they've said to you that we've replaced these all the time.
No, I didn't even see a report from them.
Okay,
I saw nothing from them whatsoever. Which is
possibly one of the things that was interesting, it's going back a bit of time now, was that DNOs by nature look at the individual incident. You know, they'll investigate the incident without necessarily looking at the previous 10, 20, 30, 100 incidents and looking for that.
It just seems like with meter up installers and obviously the need for things like Macopa, you'd have thought that they'd have some ability to actually put a guidance thing through for owners of systems.
Yeah, I mean, I think with the fragmentation of the industry as well, it doesn't help, because there's possibly less talking between the regions now than there used to be in there. You know, the meter operators are no longer employed by the DNOs or the electricity boards as they were, you know?
Yeah, and I do think that fragmentation has caused chaos. When you're trying to talk to someone about a board, getting a board changed. Years ago, up until about 15 years ago, the board was owned by others. And all of a sudden, one of the most recent changes is the board now is owned by the property owner. Well, okay, if the property owner owns it, how am I supposed to replace it when it's other people's equipment? And more importantly, to other people's equipment? How do I do that? And when was I ever spoken to about accepting that responsibility? I'm not talking about just a workplace, but a home. Somebody else owns my meter board.
It just feels like retracting liability as much as you can, and then getting, adding that we must install outside as well,
without cooperation, consultation, or anything on the duty. So we'll get onto that in a minute anyway. But again, some more images of just more cutouts. As you can see, the damage, it can destroy homes, it can destroy lives. It's something we need to be very careful of and aware of. We thought we'd just use a range of images really just to show.
What is the first sign of this? Is it heating, creating maybe some pitch seeping? Is it the sound of arcing? Is it the smell? I mean, if electricians are asked to come and look at something, and then they don't get the right information from the client, and the client actually points into the fuse, So the electrician doesn't actually, get, instead of getting the supply, they get electrician in. What kind is one of the first things that they would actually
what would you
see?
It's a really good point, and it's one of these things that we operate nowadays with the insulating gloves. Whereas in the old days, I think there was always a technique of putting the back of your hand onto the cutout before you actually pulled it, and it was based on a temperature sense as an experience thing rather than anything else. The requirement now for the guys is to use the voltage indicator to try and touch that, but it can be so localized. You can go through that process of doing that.
Well, it's an insulating material, isn't it? So it's going to have lots of
for the breakdown. Yep. Yeah. But as far as the customers go, you generally very lucky if the customer smells it if it's in a cupboard and it's buried. But if they do, they report that fishy smell. They'll hear crackling. And they'll generally get to the point where it's breaking down, where the lights are flickering and things like that as well. I actually remember one specifically where there was no longer any metallic contact between the cable and the house, but the house was still on supply.
Wow.
That's how conductive the material got. Flickering lights, the customer had phoned in because the lights were flickering, but it was at the point of almost catastrophic failure. But the boys got there at a particular time where it was still in supply.
So it's just a block of carbon between the two.
Exactly.
Exactly.
And it has that knock-on effect because the temperature, as I say, it's 1,000 degrees for the components of the cutout cell to fail, but the PVC and the cables above go 100 degrees or something. So there's that knock-on effect. You've got them all crossing each other, and the insulation goes in the cables fairly quickly. And you'll see in a lot of the investigations, the finger will get pointed directly at the cables, a slack connection, or they'll look at the cables as being, the cause of it, when primarily the cause will have been the failure of the connection within the cutout, and then the subsequent tracking.
Was there a certain time where a lot of the finger pointing was loose connection cable, but then there was more of an awareness, and they go, actually, now it is the phenolic material?
Yeah, there's still, there's still what we did specifically was we were recovering the badly damaged ones. We weren't looking at a bigger picture, so we weren't going out and surveying hundreds of phenolic cutouts in order to establish, how many were failing. We were looking exactly at the cause of failure. So the ones that were failing in the worst way were the ones that we were spending the time looking at to establish what was the root cause of the failure. And that's where the tracking thing came from. That's where we got the information for that. So we had a very narrow, very focused look at this. But up to that point, any jointer or any electrician that's worked in this industry will have thrown hundreds, if not thousands of them in the bin in that condition that you can see on the screen at the moment, and just basically dismissed it as a slack connection.
That's a connection, yeah.
And that's what worries me, because I have opinions on testing this, but we've got a video later on, so we'll just move progressively along. These are visual aid stimulators. This is a nice little video, Paul, if you press play. So this is obviously a little cabinet meter box with a 60 amp fuse, and you can see in the video that there's smoke being emitted from something or another burning or melting and being exposed to extreme heat. It's
yeah, right. You can see that. You can see it, Paul, just above the phase conductor there. You can see that
the heat build up.
The heat build up. It's similar to the board you've seen previously. There, it's very localized there. But that tracking, the tracking that you worry about there is between that top terminal and the neutral terminal next to it, because that won't operate the fuse until there's a significant bit of damage, and it's worse in the incoming side because you've got to operate a substation fuse. And it's a high resistance thing, so it starts life as a very good insulator and a very high resistance between the two component parts. But then very quickly, as that deteriorates, that'll deteriorate to the point, of almost a dead short as we're finding them.
Yeah, I think we'll get onto that, some other options for testing. But Dave, I still think you need to update your testing webinar. You can see a future one coming. This is an interesting little a snippet from a document where it's GRP versus phenolic. I'll read it out for everybody. Both materials are capable of good service performance when properly installed and used in reasonably clean and dry conditions. Product failures, of course, occur if installation conditions are not correct. We call it external influences in our world. If, for instance, a cable terminal screw or fuse clip is not tightened correctly, leading to catastrophic overheating, or if in damp conditions, perhaps coupled with conducting contaminants, leads to a loss of insulating capability. It is under failure condition that marked differences occur between phenolic and GRP house service cutouts. Phenolic suffers from an intrinsic material characteristic, as Paul said earlier on, which can be self-destructive, namely tracking. When the material decomposes, because it will over time, and it's heat strain and all that good stuff, for example, due to arcing or surface leakage currents, it forms carbon. The carbon readily conducts electricity, leading to reduction in electrical creepage, which we need to be very wary of when we're designing any form of electrical product. Heavier leakage will enhance carbon formation and self-propagation failure. GRP, on the other hand, will simply not track, at least below 1,000 volts. And our grades, by virtue of the fillers used, are particularly resistant. Now, this is really interesting because the bit about GRP, Dave, you and I both know that technically, if you're not cleaning or maintaining your GRP, is not true.
I'm going to say it depends on the condition of your GRP.
And the size of the electromagnetic field and the voltage approximate to it. I have some recent examples, but I'm not going to go into that. That's for another webinar. So GRP, if you are using it, folks, make sure you keep it clean. Remove those surface contaminants. Now, we're not asking you to get a damp cloth and clean down a DNO intake, but we will come on to what you can maybe do later on to maybe help prevent this sort of stuff and be a electrician.
This is where we saw the vulnerability in those cases that we were reading back with all those examples where there were those 5 cases. One of the things that was evident in that paperwork was because they are idle devices, there seemed to be some level of excuse for the lack of maintenance and the lack of consideration for them. But an idle device will still be subject to severe different change of demand, of environment, of heating, of moisture, as it goes through the life. If somebody changes the way they use the space, or they use the demand.
Well, could I just make a wee point on that previous slide again, if you could go back to it? I don't know if it's possible.
Of course you can.
Just in the first, the top paragraph there, product failures, of course, occur if installation conditions are not correct. They then go on to describe almost, the typical domestic installation conditions, damp conditions, we were seeing these failures in very, very typically domestic conditions, but you could see where moisture was playing a part in this as well. And this wasn't, they were not damp conditions, but I think there's a thermal cycling type of thing that's attracting moisture into the phenolic cutout, and the cutout itself has the ability to absorb a certain amount of moisture as well and retain that moisture. And that was again contributing to the tracking and the failure as well. So it was just something, that particular paragraph, it was one of these things that we tend to think that it must be a terrible condition. These only happen. They don't. They were happening in perfectly normal domestic environments.
Yeah, I do think the one place that you can lead to catastrophic areas is underneath the stairs, because I've seen plenty of houses where they've insulated under the floors. You go underneath the stair cupboard and it's freezing cold. The intake cable's coming right under an air brick, and you just get condensation and all sorts. So yeah, understair cupboards are an interesting place, but let's move on. So part of the research, always research, try and get your facts together. And again, this is us as 5 engineers chewing the fat over an issue that is slowly disappearing, but still can occur. And I think, Dave, in one of our earthing podcasts, you quoted some old statistics of number of fires on electrical intakes.
We did, and we also quoted the study that said a legislation is supposed to put the need for maintenance to avoid that. But this applies here as well. But that
hasn't happened.
No.
So one of the things we did was, I'm a railway chap, so there is some references to phenolic, because we have tried to research and go to ground a lot on definitions of phenolic, and many people use it for many, it's the chemical engineers and the plastics industry, they use it, and there's lots of different ways of using that phrase phenolic and phenolic materials. But interestingly, there's another term we wanted to use called silver migration, which was used in railways, and they actually did define phenolic as a breakdown which led to silver migration, which effectively led to silver or silver plated contacts and moisture and an insulating material, and how black relay bases could cause signalling failures and all sorts. So they're interesting reads. They're railway group standards. They've obviously been withdrawn because there was an edict to remove them all from signalling so they didn't cause any crashes or disasters. But it's interesting to see how it's not just in the domestic cutout world, it's everywhere. These materials are still everywhere in many places. Move on, Paul.
Well, this goes on to cover a bit of silver migration.
It does. Henceforth, I'm pointing. The movement, oh, no, go back. So some of the bits in this railway group standard, silver migration defined the movement of metallic silver over and through insulation is most commonly encountered on relay plug boards within certain relays and plug couplers. Initially, it is restricted to the surface, but within time penetrates into the structure of the material. It can conduct electrically and is able to bypass contacts in circuitry and introduce connections between different circuits by forming a bridge between adjacent contacts. That's what it was doing on signaling, giving spurious and false signals. So you can see why they had to remove these bases from signaling. Onward we go. And then obviously their definition of phenolic at that time of writing these standards was thermosetting plastic made from a phenolic resin with wood flour filler. Moving on. One of the other interesting comments in it is insulating material which can absorb moisture, such as phenolic compound, will accelerate, but it is not prerequisite for the process. Plug board spaces and plug couplers made of phenolic compound are always colored dark brown or black, as Mr. Ward said in one of our previous DNO videos, also known as Bakelite, or as Paul has said, what was it?
Paxilin.
Paxilin, yeah. The thing is, Paxilin was banned on railways decades ago when I was an apprentice. I loved it, but then they banned it. Don't ask me why. It was something to do with asbestos content, but I never got any evidence of that. Anyway, moving on.
Certainly.
If his computer works.
I'm being a naughty boy. I've lost my mouse. It's run away. Got it.
No, there we go.
We've got another video for those watching, but we'll narrate the video. And it's basically very simply, well, in fact, Gordon, do you want to tell us what's going on here?
So effectively, the cut itself was recovered from site, having given a positive indication using a voltage indicator. On this occasion, we measured the surface of the cutout, i.e. the cutout fuse itself. We directly went to the neutral bar, and as you can see, measured on a, I think it's a 500 volt scale there, and I think it's measured at full mains voltage on that. Thing, so you can see that there on the scale.
I'm trying to stop it on the. You can't quite see.
No, so we're doing a 500 volts IR test.
Yeah.
Yeah.
It's not an insulation, it's just purely a voltage. It's just a voltage indication there between the neutral and the live. So it's connected up live and neutral.
Okay.
And the guys are using that as a voltmeter, nothing else, voltmeter, and he's basically touching the surface of the fuse and touching the neutral bar.
Okay, so it's an insulation test, but they're using, so what's scaling there is voltage.
Yes.
Okay, gotcha.
Yep.
Looks around about 200 volts. Is the bottom scale of voltage there?
I think it was half deflected. I think it was on 500 volts and it half deflected. So it was full mains voltage single phase. So it was about 270, 240.
Just to be clear for me being a complete idiot here. So we went on the neutral and on the surface of the fuse carrier and we got 200 volts.
Yeah.
And for those listening, when we say on the neutral, we're talking about the actual carrier material that's over those conductors, not the conductors.
So so we've removed the neutral cover there so that we can actually touch the connection.
So one point is reference to a conductive material. So we're effectively proving that breakdown in insulation value. And this is what we were saying about testing. Now, as an electrician, if you could visually see a cutout and you're worried about it, maybe something as simple as a low impedance ohm meter or an IR test across certain points may give you, or even that touch potential test that's built into the Mega MFTs now.
Yeah, but technically, if an electrician is just doing a EICR and he wants to read the rating of the service fuse, he may quite easily touch the service fuse to try to peer around and see if you can see the amps on it, on the holder. He may touch that, and if he's touching a reference of an earth and he touches that, he will you'll feel that.
Yeah, but we'll move on. So
that's another hidden test for me. Thank you,
Dave. This is a test for you. Honestly, I've got a list in the back of my brain. Moving on, published in 2013, there have been 21 editions of this published. the MOPCOA, Guidance for Service Termination Issue Reporting. Now, this is hysterical, and I don't mean any detriment to MOPCOA. This is a fantastic document, but it's amazing how we see things differently. So this has some coding. So Paul, if you just plug along, one of the things it does have is a very good visual indicator on the what is the customer equipment, what modern DB equipment is, and who owns what, the supplier, the customer, and the distributor. So it's a really good document. It's available for free. Please Google it.
Can I ask who authored this?
Yes, MOPCOA. Sorry, not MOPCOA.
So that is an organisation themselves, is it?
Yes, they are. Yes, okay. They are the metering organisation.
Meter Operators Code of Practice Agreement. So it's that's up there. But that particular document was done in conjunction with the Energy Networks Association.
With the ENA. Okay, I had a feeling ENA were involved with it.
They do the quality assurance and checking of it. Moving on. So they have, you might recognise those watching, some codes. But rather than C1, C2, and FI, C3 and FI, they have a Cat A, Cat B, and Cat C coding system. And for those listening, I'll read out. A Cat A is obviously an emergency code, which is an issue with the condition of the distributor's board equipment that poses a danger, including danger of death or injury to persons and a danger of damage or destruction of property. So I think this is equivalent of our C1. You must report immediately to the distribution board by telephone whilst you're on site. Okay, so sorry, distribution business DB means. So that's a Cat A, or what we know as a C1, I suppose. Cat B, remedial work. It's an issue with a condition of the distribution business equipment that provides metering work, include meter installation replacement, from being carried out. So this is where the meter operator comes along, as I found a couple of weeks ago. Guy comes around to change a meter, puts a clamp meter on the earth, got diverted neutral, puts it on the neutral, and has still got that. Now, the minute you remove that meter, you've potentially got an open neutral there. You've got potential on the end of that neutral. So he refused to do the work, which was good on him. But it's quite an interesting mindset, to be honest with you. Pull the main fuse, put a clamp meter on the earth, got current, put a clamp meter on the neutral, got current. Remove the meter, boom, you've got a big short. So remedial work kind of stops the metering guys doing their thing. And then Cat C, asset issue or information code, which is an issue of information on the distribution business's equipment that is neither in a Cat A or a Cat B. Now, I find this is where I disagree with it personally. So if we move forward, I'll tell you why.
Certainly.
So for those who are visually watching this, Cat A equipment, we've nicely got them all displayed for you. They have codes A1, A3, A4, A5, A7, 10, 11, 10, 12, 14, 15, 17, 18, sorry, 19. And some of the codes are DB equipment, distribution business equipment overheating, defective fuse carriers, so immediately dangerous, physical damage to distribution business equipment. But the last one, A19, surface voltage found on plastic cutout. Thank God it's a C1. Now you just push the button, Paul, along. We'll show you what the category Bs are, which it appears is remedial work. Again, fuse carrier welded into cutout base, cutout loose. I think we as engineers would probably start to now argue what would be a C1 or a C2, but it's not for us. This is the Meter Operators Code of Practice. It's what their governance is. If we go to what a category C is, Paul, next one. No expense spared on these visuals. Signs of bitumen compound leaking, because it's a slow and ongoing process. Lower rate of fuse. A lot of people seem to wonder why they can't get 100 amp fuses, and they don't realize that, 60 was a big thing 30, 40 years ago. And now my local DNO are actually refusing 100 amp cutouts for EV, as I was told last week, because they've got to protect their network. Weren't designed for it.
Yeah.
Interestingly, where is it? C17, black plastic cutout. Interesting. Go on, Paul.
It's the 18th century one's got a rewirable cutout fuse.
Yeah, but move on and we'll look at why. Because, oh, look at this. Look at me, eh? Oh, look at the visual. So if you're listening to this, apologies. I do get excited by the visuals. So what they have in this MOPCOA guide, and it's very good, is it's a journey of knowledge. It's free education. So they have a nice little, almost a safety bulletin, where they talk about the asset condition code, and surface voltage on a plastic cutout is noted as a potential safety issue, has been identified with single and three-phase black plastic cutouts made from phenolic materials, installed by distribution businesses across the UK between 1967 and 1992. I think, John, we'd probably maybe argue with those dates from 67 because it's probably older.
Yeah, I mean, they probably don't want to admit that some of the stuff's that old, but yeah, plenty of metal before that, but take them as approximate dates anyway. So
yeah, there is. It then says whereby plastic casing in some circumstances can become conductive, leading to a risk of shock and or excessive heat. Exactly what we've been discussing. So this is not us making stuff up for those people who may think we're making it up. It is part of your risk assessment, and that's really important. Guys who work in metering and for the DNOs have to do dynamic risk assessments all the time. Got to keep on your toes. I can't see it, I can't smell it, I can't hear it. You touch it and it kills you. If as part of your risk assessment you identify the cutout as plastic may contain phenolic material, before the operation, check for surface voltage using appropriate contact voltage, direct contact. If a sustained voltage is found, record the voltage value, report it to the business. Reports are based on reading from a single point of contact voltage indicator must be confirmed by a second. So once you've found surface voltage, you then check with a voltmeter. If you're uncertain on the interpretation, contact supervisors. And it says a proximity voltage. So those glow sticks electricians use, they're no good. You need a surface one. It then gives you actions. Do not continue to operate. Keep the area clear. So keep people safe. Ring them up. Report it as a code A19. It's a great piece of information. However, C17, what's the difference?
So the difference with C17 is the asset information. What the DNOs were looking for was information that would allow them to build remedial programs. So some of the codes that were in C17 were age/asset related, so that fundamentally, if we go for funding on a phenolic cutout replacement program specifically, then we've captured all this C17 information and we would be able to build programs accordingly, or scale the size of the program based on what we'd found and how many were actually still out there.
On that,
so A19 is safety related as a reactive action to the presence of a surface voltage on the plastic cutout. C17 is a active strategy to collect a asset log to identify where all the plastic cutouts are for management.
Yes.
Okay.
And other items. I think there's for pyros and things like VIR cables and things like that as well. So things that we would want to.
So a plastic cutout is C17. Check for the presence of voltage. It then becomes an A19.
Well, here we go.
No, I've learned something new. And you're absolutely right. Actually, it doesn't state if I think it says when no surface voltage is recorded. So naturally, it's the equivalent of a C3. Improvement recommended. Put it on a log. Do a rolling program of replacements. It reduces the risk to the distribution business. It's common sense investment and management. It's
a good action. I mean, fundamentally, the meter operators are the real pivotal role of persons who are going into people's homes, although, as I say, not into mine because of the way my provider works. But if that's the action they need to collect a record of where these cutouts are, then that's what they're doing.
So one of the things that it's worth noting on this, because obviously there's only so much research we have on this, is an interesting side. I think we've spoke about it before. Where an external, I don't know why the codes are on there, that's my error. An external intake position in UK power networks is preferred for a certain reason. There was a Southampton Coroner Rule 43 to minimise the use of internal metering equipment because of fires, failures, etc. So for any electricians or learners who are wondering why the DNO cutouts are outside, it's mainly to protect the internal if there is a breakdown or a failure or a fire, and it's common sense. But interestingly now, if you wanted one inside, you'd need to get written permission from the Director of Asset Management if you wanted your DNO service head inside, like the letter from the Pope, basically. So it's worth noting. You can see kind of the background why they make these decisions. Mr. Skirm, next slide. I think we're just back to that wonderful video to kind of just summarize and finish it off. I don't think there's much more really. I think it's just more of a kind of what do we do to for electricians to keep safe with it. I think it's, as Dave has rightly pointed out, there's some hidden tests here. There's some.
I mean, is there a way an electrician can? If an electrician's wanted to be proactive here and they identify plastic cutouts, is there a way they can help notify or update the information with the records of the network provider?
I think the usual any signs are heat, burning, bitumen leak and that type of thing, you would expect the guy to report that anyway. I think the recommendation for the meter operators is probably as good as you can get as far as allowing the guys to operate as safe as possible with the voltage indicator and, you know, doing the test. I think you need to be, when you're training people on that though, you don't want them to limit to one stab in the middle of the cutout and that's them done their job. You really want to explore the cutout in a wee bit more care and where you place the voltage indicator to give you some sort of indication if there is a breakdown occurring. It's not always obvious that, you know, you can, some of the ones we recovered, you can see in that one the shines away on the area just next to where the tracking occurs. And sometimes that was fairly obvious, but in others it wasn't obvious at all. And I think the point that the British Rail one moved about it going through the material as much as on the surface, that we found that case as well. So it's no something that's always immediately obvious or can be seen even using the tester.
So with if a Sparky found a plastic cutout and waved his voltage indicator all over it and got nothing, and got his voltmeter out and connected it to Earth, because he's not likely to get access to the neutral terminal, really, is he? So, and then he wanders all over it with his probe and he finds no elevated voltages. So he says, well, okay, that doesn't seem to have started to degrade, but the Macopa guidance says that's was it C17?
Yeah.
Is there any way of them, you know, can they then pick the phone up and speak to the DNO and say, look, I've got a Macopa code C17 going on here? Would they take any notice of a spark, do you think?
I don't think they would, and I think that's purely down to volumes more than anything else. I think they even struggled with the volumes for the smart meter rollout as well. But again, the key thing was the Cat A's. You know, you want anybody and everybody to report a sign of burning, but you know, just reporting asset condition. Locally, it happens. You know, I've probably had loads of information about VIRs and things that were really helpful to programs when we were doing modernisation and stuff like that. Staff were doing that. But genuinely, I think they would struggle with the volume if the guys were doing that. I think NAPIT did offer, and I think there were discussions with the ENA at one point about using the Cat A, B's and C's and how that would be, fed into the ENA, but it was never adopted. And I think it was just simply down to the volume of calls that they would have to take.
I'm going to give a thought before I turn this over to final thoughts, because I'm mindful of time. I genuinely believe if I was going out and finding a black phenolic cutout now and I was still doing the ICRs, I'd note it on my form. And I would, I would go away and get the MOPCOA guidance and have it in my van and use it as a source of understanding and better able to report. I would still discharge my duty even in writing. It says, look, you might want to do something about this in the future. I'm not saying you have to code it as C1, C2 or anything like that, but I would definitely, and Dave, you were saying about continuity tests, the Earth are neutral. They're all hybrid PMEs now. So in theory, you should be able to go off the Earth bar and just do some testing on the surface to see if you get something. So I don't see any reason why people can't do. And remember, if you get a volt stick and wave it around, it will glow. But you need the surface contact stick. So don't think your volt stick will protect you or your back of your hand. Actually get a surface contact indicator that the DNOs use, they're approved products, or just get your voltmeter and use the Earth as a reference and then go on the surface and see what you can find. Protect yourself is the main point of this. This is a legacy thing. There is still probably millions of these cutouts around the country, but as with anything that gets old, there are more and more instances. And this whole point of this podcast is to help you with the research that we have and the videos that we have and the images to identify it and better support your customers and keep yourself safe. On that, I'm going to go to final thoughts, and I want Mr. Mackenzie to start this one. So, Gordon, what's your final thoughts, advice to electricians doing this?
I think for me, Paul, and the opportunity to come here tonight as well was, I always envisaged myself working at a service position or working, anywhere like that, and I want as much information and I want to be as well educated and as knowledgeable as I possibly can be, and that's specifically where incidents can occur, and it's all about safety. It always was about safety, and it always should be about safety. And I think getting the information to the guys, education, all a good thing.
Yeah, absolutely, totally agree. JW?
Yeah, I think just to reiterate that what we're talking about here is that the fact that the plastic material itself is becoming conductive. So if you are going to test for that, don't use one of the volt stick sort of things, because obviously, of course, it's going to glow there because it's right next to the conductor. So it is you need an actual metallic contact onto the plastic material itself to determine that. Otherwise, if you just wave a volt stick around the cutout, well, what a surprise. Of course, it's going to light up because there's obviously the electricity in there. So that's kind of the point that need to get across there.
Very valid. Mr. Skirm, final thoughts or advice?
Yeah, I mean, these things are getting long in the tooth now. Obviously, apart from the electrical degradation, there's likely to be mechanical degradation, brittleness, embrittlement, and weakness in the plastics themselves. So it's not the sort of thing I think Sparks want to be thinking about pulling the fuses on, even if they do get no voltage readings on it, because the blinking thing could just fall apart in their hands. Think VIR cable. You know, this is the sort of the concept we're thinking about with this phenolic resin. That's the age it is now. You know.
Yeah, I think this is a bit of lost knowledge. But Dave, your final thought?
I like to role play things in my head, and I think about who is going to first discover these things. It's going to be the homeowner. It's going to be the consumer. The lights are going to start to flicker. The TV is going to go on and off. The first thing they're going to do is look over the fence, ask Doris next door. Theirs is fine. So they're going to call the Sparky, probably, not the supply authority. So the Sparky is going to be probably most often, in my mind, the first person to come and investigate this. And so this is why it's so important to understand the phenomena and what can happen here. And for Sparkies to equip themselves with the right voltage indicating strategy, gloves, and to actually do the normal process with the board. But if the supply is bothering about, as we said, just check the voltage present on that and then escalate the action of escalation. But I think, you know, we need to make electricians aware of this, because I have a feeling with especially in domestics, they'll be the first persons who actually will see it. And they may, again, if we don't talk about it more, they may go loose connection, because that is obviously in the back in the mindset the only culprit with these devices. I think a lot of electricians aren't even aware of these components failing. So it's, you know, it's a loose connection or it's a supply issue. And if it is a loose connection, they may get hands-on checking. You know, a lot of electricians, if they think it's a loose connection, they may see if it sparks a little bit by getting their hands on it, wheeling it about. And we don't want that.
No.
So we want them to check for the presence of a voltage before they do anything like that.
So,
you know,
my recommendations is to any electrician, if you're doing a lot of domestic or commercial industrial, have a set of insulated gloves, have a contact voltage detector, maybe use, I know Q-Tech and Mega have touch voltage stuff. If you've got an earth terminal nearby, maybe try and do some continuity IR testing if you're not sure. If you're in the domestic world and the customer says, "Oh, I got a tingle when I reached in to grab a bag for life off of that black thing," you know, think about what you're listening here. This is some of the symptoms towards a potentially bigger incident. So reflect back, consider dynamic risk assessment all the time, and if you're not sure, 105, and make sure you protect yourself and others. And on that bombshell, Gordon, I would like to thank you very much for joining on this wonderful little old school journey on phenolic. And on behalf of all of my brothers and pals and Mr. Mackenzie, thank you very much for watching. Thank you very much for listening. And until the next one, take care of yourself and each other. Bye-bye.
bye-bye.
Bye.
Right.
And cut.